Hi, today in this video we want to look at the pressure changes with the volume changes in one cardiac cycle. So let's look at what we have on the board here. We have three pressure graphs plotted against an axis of time, and then we have one volume graph that is plotted against the axis of time. Let us first look at what the time frame means. From 0 to 0.8, this represents the time taken for one cardiac cycle. So if you want to find out how many cardiac cycles can take place in 1 minute, that's really simple. You take 60 divided by 0.8. Next, we look at the pressure changes. Here, the three pressure graphs represent one, the atrial pressure changes. Second, the ventricular pressure changes. Third, the changes in the blood vessels that are connected to the ventricles. So think for a minute. If you want to distinguish between the left and right side of the heart, how do we do that? The hint is in the scale of the pressure graph. Looking at this with a max of 120 mmHg, we are looking at changes in the atrium, the ventricles, and the aortic pressure, because we know from what we have learned that there is a dual circulatory system in humans. You have a pulmonary circuit that brings blood from the heart to the lungs and backwards, and then you have a systemic circuit that brings blood from the heart to everywhere else in the body and back to the heart. So let us now try to figure out which graph represents which part of the heart. The orange graph here represents the ventricular pressure changes. The graph in green represents the aortic pressure. And the graph in yellow represents the atrial pressure. How do I know this? Why is the atrial pressure not the one up here? Let's reason. We know that by the time blood returns back to the heart, it is coming in at very low pressure. And when blood leaves the ventricles to go to other parts of the heart, you expect it to be high pressure. So if you analyze that and you look at the graphs, the top green graph must represent that of the aortic pressure, while the yellow graph at the bottom represents the changes in pressure in the atria. Next thing that I would like to highlight to you is, before we talk about the ventricular events and what leads to the pressure changes, we want to look at the valve events. Each time you have a change or a cross in pressure graph, it is an indication of a valve event, which means to say the intersection points here, represent valve events. So let's talk about what are the events that happens here. You have the aortic pressure. As the ventricular pressure rises above this point, you find that what could happen here that will allow the aortic pressure to also rise concurrently with the ventricular pressure. What we are seeing here is the aortic valve opens. What about as the aortic pressure decreases and the ventricular pressure decreases? It makes sense that when the ventricular pressure decreases below the aortic pressure, the aortic valve closes. Similarly, when we have the ventricular pressure increases above the atrial pressure, the AV valve closes. If you will recall, this is to prevent backflow of blood from the ventricles into the atrium. And over here, when the ventricular pressure decreases below the atrial pressure, we expect the AV valve to open. Next, let's try to make sense between the changes in the ventricular volume and the changes in the pressure. So we are going to look at the orange graph with the blue graph. So in this segment of the graph, we see that the blue graph increases from somewhere about 100 to 120. What would cause the ventricular volume to increase? Quite simply, is ventricular filling. So, as if you could imagine in your mind a chamber with a fixed surface area, as you put more liquid in, you're putting more mass into the chamber. So that accounts for the slight increase in pressure that we see here. What then accounts for this sharp increase in pressure that we are seeing over here? Now, if you match to the pressure graph at this point, in this short time frame, there is no further increase in volume. Actually, from the moment here to this point in time, there's actually no more blood coming in from the atrium. So, and notice a second thing, at this time point, the AV valve is closed. So what causes that sharp increase in ventricular pressure is simply due to the ventricular walls contracting. Given that the volume of blood in the ventricles remains the same because the AV valve is closed and the aortic valve is not yet open, there's no way blood can escape the ventricles. So in a fixed volume of blood, you have the walls contracting and pushing against the volume of blood. That causes the ventricular pressure to increase sharply. And then as the ventricular pressure exceeds that of the aortic pressure, it pushes the aortic valve opens. And look at what happens. As the ventricles continue to contract, you have the ventricular volume decreasing. And where is the blood going to? It is obviously going into the aorta. So as blood continues to empty into aorta, you find that the aortic valve, the aortic pressure increases up to a point beyond which it starts to decrease. How is that so? As the blood is pushed out into the aorta, it does not remain in the aorta. It is actually pushed to the other arteries that branches out from the aorta. So as blood moves away, you find that the volume remaining in the aorta is smaller. Consequently, it's not pushing as much against the aortic walls. That accounts for the drop in pressure. Also, as the ventricular volume is now being emptied into the aorta, you expect the ventricular pressure to decrease up to a point where it starts to drop below the aortic pressure, and then we have the aortic valve closing to prevent backflow of blood into the aorta. At this time frame here, something is happening. The aortic valve is closed, the AV valve is not yet open, which means to say the volume of blood in the ventricles remains pretty much the same. And at this point, what then could cause that sharp decrease in pressure is actually the ventricular walls relaxing. So if you could visualize a fixed volume of blood within a chamber that is getting bigger and bigger, right? As you could imagine that the ventricular walls are relaxing, that causes the chamber or the volume inside to increase, but there's no further increase in the volume of blood. This is what will lead to a sharp decrease in ventricular pressure. As the ventricular pressure drops below the aortic pressure, the atrial pressure, this allows the AV valve to open, and then if you look at what happens to the ventricular volume, it increases. So that is what you need to take away from this set of graphs. Let's try to label where the systole is. So at this point here, you have the ventricular systole. The ventricular systole refers to the part of the cardiac cycle where the ventricles are contracting. That is important in ensuring that the blood flows to the aorta. And while this is happening, notice that blood is not coming in from the atrium. Following the ventricular systole, you have the ventricular diastole. The ventricle walls, the muscular walls of the ventricles, they start to relax, allowing blood to flow in when the pressure drops below the atrial pressure. That's all for this video.